Okay, David, you want to introduce the speaker, or should he introduce himself?
So, our next speaker is known to us all. And I just wanted to say before Eliezer gives his talk on lessons from ADS-CFT, that we should all thank him for the school. I mean, I've done a little bit of work in organizing the school, but believe me, most of the credit goes to Eliezer. So thanks, Eliezer, and lessons from ADS-CFT.
Okay, thank you. I must say that I didn't realize that the organizers are going to arrange for a good blackboard today. And actually, we should probably bring the people. But I don't know if you realize how difficult it is, because they're actually also working and maintaining an institute which is 20 minutes walk away from here. And simultaneously, they also have to maintain it here. It's really tough on them. And Ofer, in particular, who is here, we have to thank for. So what I wanted to discuss, as it is a school, is actually some lessons on deeper problems related to ADS-CFT. And the things I'm going to raise are not things which you are going to hear about every day. They are not in the forefront of the research, but I think it's nice to know it, because one day you may need it, and it's helpful. So maybe you'll remember that lecture for that. So the two issues that I want to address is the issues, they can go under the so-called black hole information paradox, and they can go under the name of how do you handle a big crunch, or for that matter, a big bang. Now, the first case is a case where you have a system, the energy goes out, but the question is about the information. There's no doubt the energy disappears, but what about the information? And the basic issue involved is, can you somehow reconstruct from outside or from somewhere else a finite amount of entropy which seems to have gotten lost somewhere? That's the issue of the black hole. And the big crunch is an issue where you have an infinite amount of information, an infinite amount of entropy, which may have gotten lost. And the question is, can you reconstruct it from somewhere else? And these two issues I would like to address. And let's say a title could have been Lessons from ADS, but we heard here Eric talk a lot about emergent space, emergent gravity, let's say, even though he talked also about emergent space. But let's consider emergent gravity, and also Nima eventually will take us to combinatorics, we heard, instead of gravity, instead of space. So here are some lessons that we can learn already from a system, the n=4 system, which was called the hydrogen atom, et cetera, got lots of good publicity. So that's a system from which we can already learn on how a lot about gravity can be encoded in a system which seems totally not to be gravitational. And I'm going to need this in dealing in these two aspects, that of the black hole and that of the big crunch. Now, the main tool used is going to be the fact that one can, using ADS-CFT, learn through simple things on the boundary about things which are very complicated in the bulk. And maybe most important, that you can sometimes say, is there a problem or is there not a problem, by looking at the boundary. And then to figure out all the details, you get lost. It's not that you're going to recreate at this stage everything back from the bulk. But you know, is it a problem or is it not a problem? And this is important, and this you can learn in both of these cases. So I start with the case of what a graduate student brought 20 years ago to his advisor. Let's make it Peter West, who loved n=4 theories in London. he diagonalized the Hamiltonian of n equal 4 supersymmetry on a sphere, and he told them, I mean, it's something one can do exactly, we hear, so he did it, and then he just showed him the following entropy of the system as a function of the energy. So he demonstrated to him that at low energies, in the infrared, the entropy goes like a power of the energy, which is 9/10. I should tell you that in general, in field theory, I will describe under what conditions, the power of the energy, which the entropy as a function of the energy, always has here a power which is smaller than 1. Then he suddenly got something which goes like the energy. Then he got something which goes like the energy to the 8/7. And finally, at very high energy, he got something which goes like e to the 3/4. So of course, we never heard of that graduate student because Peter West probably kicked him out of his office and told him that's impossible. The only part I believe in your calculation is what happens at very high energy, because there I see that the entropy goes like e to the 3/4. I have a 4-dimensional field theory. In a 4-dimensional field theory, that's how the entropy should go as a function of the energy. That's right. The rest, it's impossible, because it means that in here we have a 10-dimensional theory, in here we have a string theory, and in here we have things which look like black holes. And that's not the theory we are describing. But nowadays, that student, if he ever appeared and showed this, would be appreciated very much. And would be said, well, that's what we expected, of course. And it's very nice. I mean, it's not earth-shaking, but it's nice that you were able to do that exactly. So we already know that inside a 4-dimensional field theory, a lot can be hidden. And you can have a lot of other structure which naively you would not expect. Now, I'll briefly remind you about the different regions. So first look at the field theory, and we had here a very heated debate on how do you count degrees of freedom, and we learned that it's a tricky issue, let's say, and we don't exactly understand, but one way which I would like to look here for looking at entropy, and we are not writing here A theorems or F theorems, but trying to look at entropy, is if you look at asymptotically free series or series which are in the UV conformal series, then you know what the constituents of the theory are, and you can reliably calculate them. Now, of course, if the theory is strongly coupled, it can be conformal and strongly coupled. It's more difficult. But let's now not consider these more complicated cases. So a theory which is very weakly coupled, if it's conformal, or asymptotically free, if it's not conformal, we can look at the degrees of freedom. And then if we just use extensivity arguments, then the entropy has to be the function of the space-time as written there. The energy, being extensive, has again to have the same behavior. And if you remove the temperature from both of these considerations, you will get that the entropy of the system always goes like the energy to a power smaller than 1. And if you are in 4 dimensions, it should be 3/4. If you're in 10 dimensions, it should be 9/10. And these are the two things we saw in what that imaginary student has calculated, one in the UV and one in the IR. And from here, by the way, it's not so clear to me why the bound of information content, when we say that the entropy must go like a power, the energy or less, why is it so impressive? Because we know it from field theory that that's what it should do. Now, what is the one caveat here? The one caveat here that this theory really should have a finite number of scales in it, so that there is an energy from where on we are beyond all the scales and we can ignore them. This is not true in string theory. In string theory, we have heavy particles even with momentum 0, no matter how high the energy is. So we have an infinite number of particles which can come up. We can never get rid of them, at least in perturbation theory. And therefore, in string theory, it's not obvious that you have the same counting. And indeed, if you do the free string theory, we know that the entropy goes like the energy. Now, if you go to black holes, you can look at Schwarzschild black holes in a flat space. You can calculate their entropy You can calculate the Schwarzschild radius by the same considerations I've discussed before, but using the Bekenstein-Hawking-Gibbons ideas. You calculate and find that the entropy of the black hole goes this time as a power of the energy which is larger than 1. Now, if you remember the definition of the specific heat, for example, then you realize that from here the specific heat will be negative. That is, that these objects are not stable and that actually they decay, and if you want to have some stability, you have to build special boxes for them where they can equilibrate with radiation. But it's not simple to do that. So these were the 3 ingredients which we discussed before and which we saw in the system which is n equal 4 and which is used for ADS-CFT. Now, what I have shown before is what is called the microcanonical ensemble, because I have diagonalized, or that student has diagonalized the Hamiltonian, and he didn't enter into concepts like temperature, really. The temperature was derived. You could derive it by diagonalizing, looking at how many states you have at a given band, and then taking derivatives with respect to the energy. This would define a temperature. But there is also the canonical ensemble, and when you do a canonical ensemble, you get other results. So first, how does the temperature look as a function of the energy for n equal 4 system? So it starts like a field theory, a 10-dimensional field theory, which is funny that it's embedded in 4, but it's there and it's a field theory, so the specific heat is positive and the temperature increases with the energy. Then it reaches the string region where the temperature is more or less fixed. There are discussions, are you a little above it, are you a little below it, but these are details now which I'm not entering into. But eventually, when you do by entropy considerations, you say the system will turn into Schwarzschild black holes, the temperature is going to start to decrease as a function of the energy, and this is the area of the negative specific heat. Now, as one goes on, and as the black holes which form become larger and larger, they begin to feel the fact that they are actually living in ADS and not in flat space. And when they reach a scale which is of the order of the curvature, then they actually turn into Schwarzschild black holes inside ADS. These are different creatures. I won't enter now into why, but they are different. And for them, once again, the specific heat is positive, and the energy is the temperature is a monotonic function of the energy. So if you look at this system as a whole, you see that actually, if you remember your undergraduate thermodynamics, this system invites a Maxwell construction. And actually, if you look at it from a point of view of a canonical ensemble and not a microcanonical ensemble, you're going to have a first-order phase transition between the phase here and then directly jump to the phase here. So that intermediate phase, which I discussed, will not be evident in a canonical ensemble. It is there if you diagonalize the Hamiltonian, but you don't see it in the canonical ensemble. This, in the bulk of the system, is called the Hawking-Page transition, and it will reflect the 2 phases which the system can be in the bulk, one the thermal ADS, and one the black hole in ADS. So if we look at the system, we give it a temperature. We're doing a canonical ensemble. We could have thought we are just sitting in ADS, and this would be ADS. The topology, it has a non-trivial pi1, which this is Euclidean space, so it has a non-trivial pi1. On the other hand, what you learn that there is a phase transition, a first-order one, and the system then can become a black hole, which has where the pi1 is kept at the edge, kept CAPPED, and that system has changed its topology. So this issue will play at least an intermediate role in discussing the black hole information paradox. So you look at these 2 things, and en passant, if you wish, you answer the question which bothered people in the 80s, and that was, we have moduli spaces, and we ask ourselves, okay, what string theory are we sitting in? And in particular, like if you remember from many years ago, the Klein paradox, you ask, is it possible in a relativistic theory to have, can you conserve the number of particles or not? And the answer was that the moment you have any interaction, you cannot conserve the number of particles in the system. So the question which people, as I said, in the 80s, I remember David wrote a paper sometime in the 80s, the question was, are we forced to mix topologies? or not? Can we just live in one topology? And the answer which we got from ADS-CFT is that if ADS-CFT is correct, and we have lots of evidence that it's correct, in order to enforce it, one needs to have a mixing of two different topologies. They have the same conformal boundary, but inside, you see that the topology is changed. So the issue of is there topology mixing or not is not something for a debate. Like in the Klein paradox, you have to accept it. There are situations where this will appear. So these are some facts that we are collecting about the system. Now let's gradually, we will try a little bit more to move into the bulk, but then we'll go back to the boundary. So this is a spectrum, more or less, of the CFT. And this CFT has high energy states, which are densely packed, representing the black hole. And they come with density n squared over r. And here you have, at low energies, states coming of order 1, largely spaced. And they come with energies 1 over r. And that was one of the reasons why you needed topology mixing. Because on the boundary, you have a theory with n squared degrees of freedom, which is n equal 4 Young-Mills. No matter weak coupling, strong coupling, the n squared is there. The exact dependence on the coupling is trickier, but the n squared is there. And this you cannot get from the part here, which represents the thermal ADS. And therefore, because that gives order 1 entropy. So that was the thing which forced to mix also the black hole. Now, in general, we are going now, when we are going to discuss the issue of is there a black hole information paradox or not, or let's say, not discuss it, but following, in this case, I must say, the work of Juan Maldacena influences all what I'm going to discuss. So the question is, can you formulate in one precise way the black hole information paradox, which is complicated? There are many formulations of it. Many of them are imprecise. They sound interesting, but they are not precise enough. Can you find one? And doing that case all the way, can you learn if you can punch an argument in those who claimed that there is a problem there? And if the moment you punch a hole, even if the problem turns murky afterwards, you are quiet at least that there is that the problem solves itself. And that's what I told you, that this is will be one example where learning from the boundary, you will get an answer. You won't get the details, but you will know that you don't have to lose sleep anymore on that problem. You can lose sleep on other problems, but not on that particular one. Now, I'm going to talk about something which is a very small effect. Tiny effect, it's unimaginable how small that effect is. And nevertheless, it's going to be important in order to answer the question. And as the school has also had not only mixed topology, but also mixed with experimentalists, I want to bring you an example in the history of science from the 70s, where actually something which was very small, looked totally insignificant to most people in the field, actually turned key. And that was the issue of the fact that there are no flavor-changing neutral currents. So at that time, I was around. I would have gone to the school had it been there. And I'm sure that in that school, actually it's not obvious if anybody would have discussed it. There were so many issues floating around. And to focus on that particular process and say, oop, that's important, that there are no flavor-changing neutral currents, required a lot of intuition about what's important in nature and what is not. And nevertheless, from that phenomena, Jim, Glashow, Iliopoulos, and Mayani learned that there should be another quark, the C quark. And it looked a very roundabout way to find something so fundamental, which is there exists another quark. And remember, that was the fourth quark, and that was a period when people were not so generous in adding quarks and adding quarks. Neither was they generous in adding leptons. They thought a muon is already enough. We don't need a tau. We don't know what to do with a muon. And definitely we're not looking for more quarks. But these gentlemen said, look, we have this tiny, very tiny thing, but this is a crack in your theory. So you have to put something to fill up the crack. So this will be in the same, from the same point of view. So as I said, I'm reviewing again. I'm adding now, I'm reminding you that when we have D equal 4, N equal 4 super Young-Mills theory, it is that its bulk description is given by ADS 5 process 5, and you also have to take into account, if you are at finite temperature, also at least one more configuration, which is the black hole in ADS 5 process 5. Actually, as far as I know, there is no theorem which tells you that there are no other configurations which you should take into account as well. But these are the ones which have been identified and are used. So as I say, the CFT, we remember, is bigger than just ADS, but we also should remember it's also bigger than just the black hole in the bulk. And I write below, I remind myself that as I change the temperature, a phase transition occurs. At low temperature, the black hole is singular in ADS. It can't form. When you reach to the order of the curvature, it can form. In the beginning, its free energy loses, but then eventually, after a small change, it dominates over the thermal ADS. So here is some kind of primitive dictionary about the things we are going to need about the relation between the boundary and the bulk. So if we have a finite temperature equilibrium state, it belongs to a large black hole. Then there are subsystems which can decay into hot gluons, which are related to small black holes in ADS, which have negative specific heat. And then the large black hole has order n squared states, as we described, high energy n squared state, while thermal ADS is just related order 1 states. Now the original formulation of the black hole information paradox required, actually, it's much more natural to do it with small black holes. Because there you can imagine how they evolve into a how matter evolves into a black hole, and then how it evaporates. While for large black holes, this is an eternal black hole, so it's a different story. But unfortunately, we haven't yet developed the tools how to handle small black holes. So we are stuck with looking at the problem with large black holes and trying to understand what happens there. So the way that you handle the system, I mean, you can think of many ways, but a way which turned out fruitful to be able to formulate a problem was the following. You said, let's look first at the thermal theory on the boundary. From there, as I told you, we are going to get the right answer for something. And then we are going to try to reproduce the same problem in the bulk. So the question is, you have a system, it's in thermal equilibrium, and just try to disturb it a little. And try and see what happens to the correlation function as in this thermal ensemble. So rho is the density matrix related to the thermal ensemble. And you want to know how this correlation function behaves at large times. Now, the issue that we really want to do is to study the initial bulk state and see how it evolves into a final bulk state. But that's too difficult to do straightforward. So we go to the initial CFT state. We ask how it develops. And this is the question of looking, for example, at that 2-point correlation function. And then you go back and ask, what does it mean for the final bulk state? And in this roundabout way, you learned how the bulk state evolved. OK, so for here, I'm going to now to tell you some things which are just correct. So it's nice to know about them. I mean, they can go under many headings. It's very nice to read, actually, papers of Michael Berry, which I think were mentioned also by Eric, where you learn that the large T limit and the H bar goes to 0 limit is a tricky. If you try to commute the limits, they're rather tricky. And this is one manifestation of this fact. So there is a following statement. Classically, if you have a system which classically has a compact phase space, and in that system, classically, there is volume conservation, like we learned in classical mechanics, Or if quantum mechanically, we have a system which has a discrete spectrum, that is, the spectrum is gapped, and it obeys unitarity, then if you, how I think Regan said it in once about redwoods, you've seen them one, you have seen them all. Here I would say Humpty Dumpty can come back together again. In other words, if you have a system which obeys these assumptions, and you look at the correlation function of how a certain correlation function behaves at time t, and how it compared to how it behaved at time 0, then the correlation, there will always, no matter what epsilon how small epsilon you will require to be, you will always find some time, which is related to epsilon, where the correlation function at that time t of epsilon will be very near to the original correlation function. So that's what I said, Humpty Dumpty comes together again. You wait a very unlikely configuration, but if you wait long enough, and I told you, this is very tiny effect, so you have to wait a lot of time, then this thing reoccurs. So just to get a feeling, so you get a feeling of what one is doing. So when one calculates such correlation functions, this is the object that one is calculating, and one is actually averaging over a lot of oscillating objects. And the question is, do you have constructive interference, destructive interference? How does this object with many energy levels, with many matrix elements, behave? And here, there is some general knowledge. These are not exact theorems, but this is a lot of experience from systems with chaotic systems in solid state physics, actually. I learned it from Max Rednitsky, but a lot of other people have done this stuff. And the behavior of such systems, of such correlation functions, are the following. There is a time, which I didn't write here how long it takes. It's a time of order the entropy. It's called, I think, the Ehrenfest time in chaos, when you do chaotic system. Then the correlation function is just going to drop down. The dissipation will occur. The function will just drop, the correlation function will just drop exponentially at the function of time. This is going to happen at times till the order of the entropy. So these are times where you don't yet feel that you have these many, many states. You are only looking more or less at your neighborhood, and you are decaying. But then, after that time, suddenly you re-emerge after what is called the Heisenberg time. The Heisenberg time is a time of order exponential of S. So S is okay, but exponential of S is really, really a lot. And the system has these resurrections after Heisenberg times. This, as you know, these features do not depend on you. I mean, it didn't depend on how picky you are on seeing exactly Humpty Dumpty coming together again. This was just a universal characteristic of the system. This, by the way, this gamma, which comes here, which in black hole you can identify by looking at normalizable modes around the black hole, this depends on the probe you put. It's nothing universal here. But the Heisenberg time is universal. Then there is another time called the Poincaré time. That time is personal. It depends on how picky you are. So if you are picky order epsilon, then you will find that in order to, for the correlation function to return a distance epsilon, it's not enough to go exponent of S. You go an exponent of S. So that's an unbelievably long time. And this is how the system behaves. So if this is a characteristic which doesn't depend on you, and then if you put yourself in the problem, you will identify also those points where the system comes with the accuracy you want. Okay, now we gradually are trying to build an order parameter which will have the property that to all orders in perturbation theory it will vanish. It will be a non-perturbative effect, which is good because we don't expect the problem of black hole to be a simple one. We want to expect a non-perturbative thing, which will give us some information. As an order parameter, it will vanish when something happens, and it won't vanish when something else happens. So to start to build this object, you take g of t over g of 0. Okay, here, sorry, here I've written on the blackboard A that gamma is not universal. The decay rate depends on the probe. And I gave you a way to estimate how long the Heisenberg time is. I won't repeat it here. You're welcome to look into the papers. And there is another estimate of how the Poincaré time, which is an exponent of S. Here, I want to look at the object L of t, which is, one takes g of t, divides it by g0 of t, takes absolute value squared, because you saw there are all these phases turning around. And what you're really asking is, look at this quantity. What is the limit as t goes to infinity of 1 over t, integral from 0 of t of L of t? Now, what are you measuring by that? So I told you a story that recurrences occur. But you want to get a feeling of the measure, how many times they really occur. So you could imagine that you have to divide this maybe to get a non-zero result by t to the 100. But it turns out that it's enough to divide it by t. And in that case, you can prove, there are some assumptions. As I told you, this is not a closed subject. There are assumptions which go on the probes. What is their structure in the energy basis? And things depend on that. But you get a lower bound to this quantity L bar. It must be of the order of the exponent of minus the entropy of the system. Now, the entropy of the system, we said, in our case, goes like n squared. And n is very large. So this is a very, very, very small number. But it's not 0. So the question you want to ask is, how does this manifest itself in the bulk? Because we know the answer from the boundary. We put the theory on S3, so we know we have a gap. We have no indications of any anomalies in unitarity for n equal 4, so we accept it to be unitary. So we are within the conditions of the theory, and therefore, of the theorem, and therefore, we should get a bound of the order exponent of minus s. Now, if we look at the number with entropy going like minus n squared, and do here the translation, which I don't have time to repeat all the dictionary of ADS CFT, but n squared goes like 1 over g Newton. So what you see is that from the point of view of the gravity coupling, this is a non-perturbative phenomena. If you want to think in another way, if you do scattering of gravitons, which should help you reach equilibrium, they go to the power s. So what one really has here, like in non-perturbative phenomena, when they are non-perturbative, instead of coupling in g, we have exponent of minus 1 over g. Here, the natural coupling in graviton scattering is 1 over s, but the result goes like an exponent of minus s. So it's a non-perturbative result in terms of the perturbative parameter in the problem. Okay, here again is to give you a feeling on what the calculation means. So this is what you need to do. You just use the fact that you know how in a unitary theory operator changes in time. And then you need to sum and average over a lot of terms. And you see that it must be that the structure of the matrix elements of your probe has some significance. So you can classify, and in a good class of such objects, the result that I told you, you get. Okay, so we know what is the answer of this correlation function. It should go like e to the minus s. And I ask you at least to carry this away from the talk. There are Ehrenfest times, there are Heisenberg times, there are Poincaré times, and on systems which have a gap and are unitary, you can calculate this correlation function and get that it's bounded by e to the minus s. So this, please remember, I never knew about it before, so it's something that may turn out useful for you in the future. Now, let's do the calculation in the bulk, because we have now a statement on the boundary. And you can actually check, which I'm not doing here, but is important, what happens if the system is not unitary. If the system is not unitary, will the result change? And you can couple this to noise and see that, indeed, the result changes if you couple the boundary system to noise. So unitarity is important. It's an important ingredient in getting this result. Now let's go to the bulk. We said that above a certain temperature, you find that the dominant configuration is a black hole. Okay, so we are having a black hole, and we are asking what happens when we do this perturbation in the presence of a black hole. So one can do that calculation. One can do it in the background of any type of actually simple metric. Again, I invite you to read the papers. I'll just tell you the general idea. You are doing what is called the Beryl-Davis calculation, namely you're doing quantum mechanics in the presence of a background, like Slava did when he did his calculations of the perturbation, how the CMB spectrum looks. And it turns out that you can turn the problem of calculating a propagator, and what we are calculating here are propagators. What you need is to calculate a quantum mechanical, non-relativistic quantum mechanical problem in the presence of an effective potential, where the effective potential depends on the metric in case. So you have to look and diagonalize this problem. Now, the effective potential in the case of the black hole has this feature, and the main thing is that it drags a little bit like Liouville, if you wish. It goes to minus infinity, and in such a potential, you are not going to generate a gap. And because you don't generate a gap in this potential, when you calculate the propagator, you are going to obtain a result which will be in disagreement with the result on the boundary. You're going to get that when you take the limit t goes to infinity, L bar goes to 0. So it goes no matter what you had as exponent of minus s, you wait a long enough time, you will be underneath the bound. And if that was a lower bound, there is a problem. Okay, so at this stage, one possibility is to look at this model and say, okay, ADS-CFT, nobody promised to us it's correct. It could be wrong. Okay, however, we have to remember that we are looking for a non-perturbative result. And when you get that the result to leading order vanishes, you are no longer excused from looking at next to leading contributions. You could do that as long as you had the leading result. But the moment the leading result vanishes, you have to look what is the next to leading contribution in this phenomena. So we do something which is, let's say, we're in the Middle East, so we can do it. It's un-American, I like to say, because you go back to the loser. There was one configuration which was the winner, which was the black hole. But it didn't deliver. So, okay, you repent, you come on your knees to the loser and say, yes, we forgot about you, but maybe you can deliver to us. So we have to take into account that even though from the point of view of the free energies, this was the leading configuration, there was also at least this non-leading configuration. And we should go and check what it gives to us. So before I told you that the effective potential in which you do the quantum mechanical problem and which gives you a spectrum which has no gap, and from that you get the consequence that L bar goes to 0, is 0 for large T. This is what happens in ADS. I'm sure you heard many times that ADS behaves like a box. A massless particle reaches infinity at a finite time. That's one reflection of the fact that you are inside a box. Actually, when Hawking and Page originally did this work, they had, as you know, G00 of ADS goes like R squared for large R. So they had, in a way, what they call the confining energy, which means that you have a very high redshift. So far apart, everything goes to temperature 0 and freezes. So you don't notice, and you succeed to create a Faraday cage in gravity. Now, in electricity, we know how to make Faraday cages. In gravity, nobody knew how to do it. But inside ADS, you actually make a Faraday cage. So this is how you get the box in the system. And once you look inside the box, you find that the spectrum is actually gapped. Once the spectrum is gapped, you can do the calculation. And you get that indeed the contribution from the next to leading term, does give a contribution to L bar, which is not 0, and it goes like exponent of minus s. So once again, you need a topology change. You needed to take into account the fact that there are fluctuations in topology, and at least you punched a hole in Hawking's argument. The hole, there are many ways to look at the hole, but one, he didn't consider topology changing processes. And here, the fact that you do consider it gives you a different answer than he argued would happen in the absence of topology change. Now, what we found out with José Barbón, that actually, even though a hole was punched in the argument of Hawking, actually, when you went into details, unfortunately, you didn't really resolve the issue. Because what L bar gives you is an integral. And it's very good that the integral obeys what you want. But now you must also go and ask about the integrand. Now, you know from the boundary CFT how actually the integrand should behave. You know what the Heisenberg times should be, and you know what is the height which should be reflected in the Heisenberg times. And here, it turns out that there is a large discrepancy between what the result of the instanton, one instanton gives, namely the changing of topology, and the result that you know is correct from the boundary theory. So from the boundary theory, you find much lower values of the function g of t. Their height is not of order 1, but of order exponent of minus n squared. And the way they get the same bound is that they are spaced in order 1. While if you put the one instanton, you actually get the opposite. And therefore, if you walked into the details, it doesn't work. But you punched a hole in the argument. So again, to repeat how things go, you calculate now a thermal fluctuation in the presence of a black hole. Rarely, the black hole becomes thermal ADS, and the dissipation here is strong enough to be able to give you a contribution to L bar, while the dissipation which occurs in the black hole on its own doesn't give it. You get the values which are don't represent the full behavior. Okay, so after one analyzed, I'm going back instead of forward. So if you imagine, let's say, the pictures that Eric was showing, imagine here is a phase space. You are moving in the phase space. Most of the phase space is a black hole. He would call it maybe the Higgs branch, or I don't know, whatever words, for fast frequencies. Then, from time to time, you reach in the phase space the area where you had the one instanton effect. And when you collect the answers from that area, you're getting from L bar a non-zero result. However, one is missing something in understanding the whole process, and that's an open problem till now, how to get it in more detail. Now, maybe it becomes a problem in chemistry, or like trying to get from classical stuff in QCD, trying to get confinement. I mean, maybe it just doesn't, it's not that simple and it doesn't work. And you just give it up. Or maybe there will be some other way to look at it. In any case, if you look at the picture here we also drew a black hole in the future, a black hole in the past. What is important was that there was this extra configuration of topology change. Now, how could you imagine that you will get a result which doesn't require a specific topology change? That would be by something which bothers me for a long time, and I think it's an open problem which we should still understand, and that is the issue of the stretched horizon. If, like 't Hooft, when he was presented with similar problems, he also had a spectrum which was not gapped, and he had other considerations, but it also bothered him. And he said, let's put a brick wall. Now, a brick wall, okay, maybe in Holland you build dams, you protect from the sea, so it's easy. But usually you try to find some motivation. Now, it's clear that something is happening near the horizon. But what exactly is going on there? What are the degrees of freedom which really could create a stretched horizon? We don't know. But what we do know, that if one would say, let's say that there is an effective theory where you summed over all topology changes, everything you have in mind, and the consequence can be represented by a stretched horizon, then you can fit and get L bar not zero, because the stretched horizon is going to give you a gap. What bothers in that is that it's done by hand. Now, a dream that I have is that maybe the phenomena there is a little bit like dimensional transmutation in QCD, or in asymptotically free series. Namely, maybe even though the theory already has a scale, but when you are near the horizon, that scale is not significant. Maybe there is a dynamically generated scale, not one which you put from outside, which would cause the stretched horizon. And if that could happen, then you could have a consistent picture of the, how to resolve the problem. But in any case, the issue of hiding, or the question is, should we get excited by the fact that behind the horizon of a black hole there is a finite entropy, was resolved. We should not be worried about it. There is a way to handle that. How? We don't know. Now, why is it so difficult? I think, or we think that one of the things it's so difficult is because there is the idea of complementarity, which is, I think, a very appealing idea, and to my mind, has something in it. Maybe when space-time will disappear, it will become much simpler to look at complementarity. But as long as we have this, I don't know, hybrid picture where we know there is space-time, even though we know we need to trade a little bit, then I think it's a useful concept. And the fact that there is a complementarity, I believe, is true, but how to be able to identify how it works exactly is very difficult. Because you need to send the probe from far away. It needs to thermalize till the horizon. It needs to reach the horizon and get terribly redshifted. So the renormalization group equation has to be taken into account, which is tough. On top of it, it must inside thermalize, scramble appropriately before it meets the singularity. And that's a very long and complicated process. And we don't know how to, at this stage, how to do a complementarity map for that. So this is the situation in the presence of a finite entropy issue. Now I want to go to an issue of infinite. But before that, I want to give a general reminder to you about how, which to me, again, is something which I hope maybe in the way Nima looks at things, maybe it will come out, how come every concept in mathematics has become ambiguous? I don't know of any concept in mathematics which, when you probe strings with strings, nature remains unambiguous. We have examples of every concept that you can describe it in 2, 3, 100 ways. So the first one, I don't know, Ofer? I don't resist. I want to show you a cartoon movie which was prepared for a popular talk and shows the issue that the metric is not an invariant concept. Namely, you can have two different descriptions of the metric. And that's just, for me, a comic relief. Yeah? No? That's another story. Here I don't need to explain. You know it all. I just want to show you the comic. Okay, quantum mechanics on a circle of radius r. Large r, small gaps. bring the doctor another patient. Large gaps. So we have both winding modes, momentum modes. So this exemplifies to you that the notion of the distance becomes ambiguous, symmetric, redundant, whatever finally the correct words are going to be. On top of it, there is the issue of topology. We know of systems which can be either described with a target space which is a sphere or which is a torus. So which is it? The string probes cannot tell. The metric we discussed. Now we can look at dimensions. And as you know, I can have small objects of the order of the Planck scale. I can have the group SU2, and that's supposed to be S3. And its dimension is 3, and I can have its Cartan circle. Its dimension is 1, and the systems are identical. Then I can go to large scales, as we described in ADS-CFT, and I can see different dimensions. I can see IR dimensions, which are 10. I can see UV dimensions, which are 4. Then there can be singularities. So the simplest case where you can have different view of singularities are the orbicircle. An orbicircle of a certain radius can just be the same as a circle. So there are two different descriptions. Once you have a singularity, once you don't. Then we learned later that the Earth may shake. In other words, we may have our coordinates non-commutative. And we may have in a different description, having them commutative, and we can't distinguish which is the correct description. Now here, what I'm bringing to you is a situation where on the one hand, you may have a picture where you are, I don't know, that's maybe one of, it actually at the end, unfortunately, it turned out to be Las Vegas. I was thinking of some exotic island, but it's somewhere in Nevada. And so you just are worryless, sitting in the pond. If you want, you can stay an infinite amount of time and calculate correlation functions. Everything is fine. But there is another view of that, which is actually a big crunch. And this is Cronus of Goya eating his son, that in other words, time was seized. So we have a big crunch. And these two pictures can also be described in a symmetric way. Namely, they are descriptions, the same descriptions of different things. And this is what I want to go now, and I'm going to discuss the big crunch. So the main, let's say, issue is before we asked ourselves, can we handle from far away the fact that we are bothered about where a finite amount of entropy is sitting? Did we lose it or not? If there is a big crunch, we lose an infinite amount of entropy. Now, in general, when singularities appear in physics, they reflect the fact that our approximations have broken down. It can mean we have to change classical physics into quantum physics. It can mean in more sophisticated ways that we forgot a massless particle. We didn't realize we integrated out a massless particle. It could be that there are a lot of non-local stuff really in the theory, which we thought we integrated out, but we didn't do it appropriately. And therefore, we feel that they are singularities. So I, for many years, was waiting for the knight on the white horse to come and save gravity from big crunch singularities. And in the last year, actually, I'm not convinced this is the case. In other words, I think that it could well be that we could handle even a big crunch inside AD, at least in the context of ADS-CFT, and it's just there. Not all, there are big crunches which we can't handle, but there are some which we can. They are there. Nobody is going to change them. Nobody is going to rescue them. There's going to be one description in which it's a catastrophe, and one description where you sit in the pool and calculate for an infinite amount of time correlation functions, which at infinity will tell you that actually there was a big crunch. But all your lifetime, you are not bothered about it at all. And I think that's a rather striking change. I don't say that the theory won't have in it a mechanism to avoid that. But at this stage, we are not sure that the theory needs that mechanism. It can live with big crunch singularities. Now, in order to discuss this, I want to use the Blackboard for a few minutes. After all, it was changed, and we can use it now. צריך עוד, איפה זה? 6. מה הוא נמצא? צריך, את זה 6 אמרת? Okay, so big crunches appear, according to Penrose and Hawking, everywhere. But we would like to study them in an environment where we at least feel we have a little more knowledge. And such an environment means ADS-CFT. So this would require to discuss a special type of big crunches. It's not the most generic big crunch. And in order to appreciate what goes on, let's look at what is, I think Michael Dine dared for 20 minutes show a landscape here. So we saw a landscape picture of effective potential. Now, in quantum field theory, we have no problem with addressing such issues. We can assume that you have some wave functional which is concentrated around the metastable, what looks like a metastable state, and we know that it sits in the same Hilbert space as the true vacuum. I guess I drew it here. And you know that you can make a semi-classical estimate, at least, at how long it would take that object to go in here. And you have a picture, a geometrical picture on how that works, which is borrowed from solid-state physics. And the idea is you are in a wrong vacuum, and you can consider fluctuations. So one fluctuation, let's call this vacuum plus, could be creating a bubble of the correct vacuum. So this is an attempt to have a counter-revolution. And now, will it work or not? So you have to, the question is, will this shrink, this thing, like the Israeli summer revolution, shrink and be forgotten? Or maybe like the Russian revolution, expand all the way and cause a lot of turmoil in the process. So it is, in this case, we know the answer a priori. We know that we are going to decay. How do we know it from the point of view of this semi-classical picture? We know that the process we are generating has an advantage that the moment the bubble appeared, there's a better world or a cheaper world in here than was here because the energy is lower. And this is of the order of the volume. On the other hand, because we have to have a transition between the old vacuum and the new vacuum, we are going to have here terms which are going to be counter-revolutionary, but they go like the area. They are related, the surface tension, which is related to the microscopic parameters of the theory, is going to describe what happens here. Now, there are various technical things which I don't have any time to go in. There's a thin wall approximation, exact calculations, so on. But basically, this is the gist of the issue. You have one contribution for the revolution, which goes like the volume. Let's call it minus, and let's say want to be negative. And then you have a contribution with some other number, which goes like the surface. So now all kinds of fluctuations can occur. And the question is, can there be a fluctuation large enough that once it occurs, it's actually worthwhile for it to grow larger and larger? And the answer is always yes, because the volume, at least after you go away from other scales in the problem, it will be dominated by the physical volume of the problem. And this will be some r to a power d, and the surface is going to have 1 power less. This is in space. So it's going, in Euclidean, it would be different with space-time. But eventually, this term is always going to win, and therefore the transition occurs. Now, what happens inside ADS? Inside ADS, the moment your scale of the bubble is of the order of the curvature, this ceases to be correct. You find that both the volume and the surface scale in the same way in terms of, let's make one scale in the problem. And therefore, the decision of if the revolution will be successful or not depends on parameters in the system. If the surface tension is large enough, the microscopic parameters make the surface tension large enough, it will fail. If the parameters are such that the energy difference was large enough to push the revolution, then it will work. So what you learn is that if you look at this field theory thing and switch on gravity, what you see is not what you get. In other words, you can be sitting here, but if the parameters of the system are not appropriately tuned, you will never go here. Okay, but that doesn't help us reach a big crunch. It's interesting to know, but it doesn't bring us to the big crunch. Okay, now comes the second question. What happens when the parameters allow such a transition? And in that case, what you find, and this appears in the original paper of Coleman de Lucia, is actually that unless you do very high fine-tuning, the system is going to reach, not here, but is going to reach a big crunch. So in the setup of ADS, the problem of looking for a big crunch is something one can try and do, because they are available there. I should tell you that once upon a time in the 80s, there were also landscapes, but less elaborate, and one drew effective potentials with discrete number of minima, and there was a hope that maybe when you couple gravity, you will find that there is only one stable one. But then Weinberg did a calculation which showed that even though in the presence of gravity these things may split, eventually everything is going to be stable. In other words, you won't, if you are sitting here at a 0 cosmological constant, the favorite value at the time, you would not go down to the anti-de Sitter even if it's lower in energy, because the parameters were such that the surface tension did build the volume. And this was a consequence of the supersymmetry. So now we go and ask the question, what happens inside ADS? And here, I'll go back for a few moments to the, did Ofer leave me, desert me? No, good. לא צריך לרוץ. So what we are going to do now is we are going to try and look at bulk configurations which one can identify as ADS crunches. We are then going to discuss the boundary theory which describes them, and a dual boundary theory which also describes them. And that is where one is going. In that duality between the two different boundary series, we are going to get the catastrophic versus the relaxed point of view of the same phenomena. And I'm going to try, in a very crude manner here, to classify in what cases, what boundary field series are related to big crunches and what boundary series are not. And I'm going to do it by looking at marginal operators, relevant operators, how relevant the operators are. And this is going to help to give us a picture when we expect a big crunch to occur by looking at the boundary series. So the generic type of ADS crunch is going to be an FRW cosmology, where one has an OD, 1 invariant, where one has OD, 1 invariant sections. That is, the matter in the problem, which is going to be added, is going to respect the OD, 1 symmetry. And what appears here in the metric, G of t, is going to obey the equations of a negative curvature space. These will be the conditions. And I'm going to show you how to construct such an object fast. And then I'm going to show you the picture, which is what I want you to remain with, on what the boundary of such a system is. Now, maybe I would like to add, let's say this would be pure anti-de Sitter. In that case, G of t would just be sine squared t. And yes, there would be singularities, and yes, it would look like there is a big bang and a big crunch, but that's fake. That's a coordinate transformation. But in a generic situation where G of t only at infinity obeys the negative, looks like pure ADS, actually there can be a big, generically there will be a big bang and a big crunch, and you can fine tune to have one of them. And this is the type of configurations that I'm going to look at. So I want to look at configurations which are going to lead to this picture in the presence of a scalar field phi, which is OD, 1 invariant. Okay, so one starts, this is a little bit along the direction of Hawking and Hartle. One starts first in the Euclidean part. And in the Euclidean part, one has, we call it a ball, which has OD plus 1 invariance, and also the matter is OD, 1 invariant. And then, in order to be able to get some smoothness, then at the center of the ball, one requires, it turns out you need to require the condition that the function f here has is rho squared, and otherwise at rho equals 0, it and its derivative vanish. And the function, as the function of matter is a function of rho, doesn't have a first derivative and has this form. So once you do that, you can look at the angular part and parameterize it in terms of coordinates theta and general spherical harmonics. And then you go to, afterwards, like in Hawking Hartle, you begin to move to a Lorentz signature or Minkowski by doing an analytic continuation of the coordinate theta, calling it I tau. And in that case, you have already cross-sections which look like bubbles, where we started here, and we are now sitting here after this change of variable. Okay, then there is a long song and dance where at rho equals 0, we need to do further continuation, and because the de Sitter sections become null, and in that case, one takes a further redefinition of coordinates, rho equal it, and y equal tau plus I pi over 2. And in that situation, one reaches the function which one wanted a priori, something which reflects, has in it a singularity, and goes to anti-de Sitter at infinity. So it can start at the wrong vacuum, because infinity in the bulk is going to be the initial state. It's the IR it's the UV of the boundary, the IR of the bulk. And this is the particular metric it has. And of course, as I said, you have to take into account also that you want G of t to go like t squared for the continuity, and you want the matter not to have a first derivative at the origin. Okay, this I think, this is one of the things you have to do yourself to get convinced it's okay. And let me show you the picture which arises here. So the region below this line is Euclidean space, and here you have SD. Then you go to Lorentzian, and here you have slices after the extra continuation, which are de Sitter slices. Later on, I will show you again how the time slices go in de Sitter, but they go from minus infinity to infinity. We will afterwards go to an Einstein manifold in order to give a different picture, and there the coordinates are going to be bounded, like we heard many times, of conformal maps, what happens. But in de Sitter, they go from minus infinity to infinity. And in the future, indeed, there is an FRW together with a big crunch. So the system has a boundary, and the boundary sits on de Sitter. So now, in a way, we are like in the situation in the black hole, where we stated that we knew there is no black hole paradox, information loss paradox, because we knew what the boundary behavior is, and it's unitary. And our job was to find how to reconcile that with the bulk description. Here, the situation is that one has now a field theory living on an expanding universe, but with time-independent couplings. And as I will discuss several times, this field theory is a bread and butter field theory. And I think by now also, I don't know by now of any reservations about having a field theory on de Sitter space. We heard from Slava a very strong statement why he believes that there is no problem to live on de Sitter. So the answer to the question, can you describe a black hole singularity, even though it has in it infinite entropy, before we try to understand a little bit how it goes. But first, can you describe it? The answer is yes. There are situations where you can describe it, because you can have a field theory living on de Sitter, and the field theory living on de Sitter, let's make the expansion not to be too fast, not to complicate things too much, so that the scales which appear in the operators on the boundary are larger than the scale given by the de Sitter expansion. So our intuition of field theory is not much different when we start on, working on de Sitter. We don't expect some non-analyticity or some breakdown the moment we switch on de Sitter. Again, I want a very slow de Sitter expansion. You can
since you started in the bulk to describe the duality.
No, the duality will be on the boundary.
You started with a bulk theory of gravity, which
Yeah.
you imagine has some UV completion. So the theory might,
Well, it's part of string theory. It's part of it's a configuration which lives, it has ADS far away. So we are used to the fact that theories which are in the IR ADS have some well-defined description on the boundary.
there are situations where you turn on some field in the bulk, which you're doing, matter field.
Yeah.
Things go wrong.
Okay, but
So I'm just saying that it's not guaranteed. You haven't found embeddedness in string theory.
okay,
Assuming, making a strong assumption
okay. I mean,
that this has an embedding in string theory.
I think this goes along. You are right, first of all, in the sense of the
For
rigor.
example, in
but-
ADS-CNT, people turn on things in order to create superconductors.
No,
Then they discover, when they go to the bulk problems, they go back and discover that the UV completion of the string theory manifests those problems.
okay, so here I think, and I don't have time, in the seminar I gave in Santa Barbara, I described in detail how I imagined the fields becoming, there was a mapping between the fields in the bulk and the fields on the boundary. And we don't see, I mean, it's just according to the standard rules. I don't see here anything happening which doesn't allow me to define, go to the long distance, scale appropriately the field, multiply it by the radial distance to the appropriate scale, get a limit on the boundary, and that's it. There is a field. These are the standard rules. Nothing forces me to go back and say there is a problem. So the field, I beg your pardon? Well, if I would see a problem on the boundary, I would complain. but I don't see a problem on the boundary. Now, if you want to see a problem on the boundary, I can create to you a problem. I'll create to you the problem on the boundary. But if I go with this coordinates, use a de Sitter slices, I don't see any problem on the boundary. And as I said, I just take the fifth dimension, send it to infinity, multiply it by the appropriate power of the radial direction, and I get what I get. That's the standard ADS-CFT. So I don't see there any...
We know the singularity inside of the black hole is also basically cosmological like this, and we're perfectly happy with
Yes, so...
that's described by a thermal state, so it's just the same thing. It's just the analog of the thermal state.
Right.
It's just
Fine on the boundary. But,
yeah, fine.
But
my problem is when you're starting with something which supposedly is sounds well defined, right?
no, I have, like Nima mentioned, I can look at the problem of a black hole, which has behind its Minkowski horizon, has a singularity. And I could say, oop, I don't do ADS-CFT. How do I dare do it? All my life I have to look for the UV completion, which will handle that.
Well, we don't actually go inside the black hole.
Right, so we go to a Euclidean picture, but we live with a singularity. And the same thing is here. I don't see any conceptual difference between the two, except, as I said, that the entropy is infinite and not finite.
I mean, you'd say the inside of the black hole is also a big crunch. It's just not
Yeah.
it's not FRW. And so you want to make it FRW.
So I don't know what the dual to the inside of the black hole is.
Well, sure, but he's not telling us that either, right?
No.
They're inside the black hole in this case.
No, we start, like you take the black hole, you go from a Minkowski space where you see a singularity, you go to a Euclidean black hole, and you do the boundary theory. Yes, the same. Yes, when I want, I go to Euclidean. Yeah, that's why I started with the Euclidean part. Okay, so that was the statement, which is okay. I mean, it's not pleasant when you see it the first time, because you want to see the UV completion, the guy coming, the knight on the white horse, but it looks prima facie that you don't need it. Now, in case you are nervous, you say, well, come on, I want to see that stuff. So how do you do that? So instead of having, and I will come back to the properties of the field theory, instead of having a field theory where the couplings are time independent, which lives on a world volume which is time dependent, we can make a change. We can do a conformal mapping, which we actually call a complementarity, and that's part of the title which appears, map, in which you go outside the system where you didn't see, or outside the swimming pool where you didn't see the big crunch, to a system where you do see the big crunch. And how do you do that? You do it by conformal mapping. Once you do the conformal mapping, the singularity is very apparent. And the conformal transformation you do here and the times you change are done in this way. So in this case, the eternity of de Sitter, and I'll show you the picture, becomes inside when you study Einstein. There you are going to see a finite time situation, and we are going to see how you see the big crunch in all its drama. Even though on de Sitter it looked totally non-dramatic. So here are the two different time slices. When you work with de Sitter coordinates, these are the times, and they go from minus infinity to plus infinity. On the other end, in the Einstein manifold, they go from some number to some other number. So you cover with a different patch of coordinates, and what is going to happen, what does this conformal transformation do to you? It changes you from a theory where the world volume was time dependent to a theory where the world volume is time independent. But on the other hand, your couplings, according to their conformal weight, are going to become, instead of time independent, time dependent. And you are going to feel the way that they behave, and you will see in that the big crunch. So let me give you now the examples of two different of various types of theory on the boundary and what they reflect from the point of view of the bulk. So once I have a theory on the boundary, I can imagine various things. I'm not allowed to add irrelevant operators. Why am I not allowed to add irrelevant operators? Because that would back react and kill the anti-de Sitter. And I'm assuming always my false vacuum started in anti-de Sitter. So I can't add irrelevant operators on the boundary. What I can add are marginal operators and relevant operators. Now, assume for a moment that on the boundary, in de Sitter, so you have a time-dependent volume, you have a field theory, which is the couplings are time-independent. What type of structure could you have? So imagine some ON vector model sitting there. If you want, you can make it a joint, but let's make it vector to look simple. And what terms would it have in 4 dimensions? So it would have a phi squared term, and it would have a phi to the 4th term. Now this, I'm thinking now, and again I invite you to look at the paper, as some Landau-Ginzburg picture, where the coordinate phi is some collective coordinate, which could have been the result of looking at branes in their near horizon limit and picking up the diagonal parts in their joint representation of the branes. So I'm thinking of some collective field phi, and that collective field phi can, on the boundary, produce something, again, which contains marginal or relevant operators. Irrelevant is not allowed. I don't have to worry about them. So now, what are the various possibilities? Let's start with a possibility where the marginal operator is stable. So at infinity, this potential is stable. Now, inside, one could imagine 2 types of situations. One type of situation is where the relevant operator, let's call it phi squared, and let's give it a large scale, because there are issues, especially when you go to the effective field theory, at what happens, what is the mapping between the microscopic theory signs and the macroscopic theory signs when the scales are all of the same order. And the order here is the Hubble constant and the radius of the sphere. So let's make the parameters much larger. In that case, there are 2 options. Option number 1, which I didn't draw here, where the relevant operator is positive as well. In that case, the CFT looks like that. And what is its property? Its property is that it generates a gap. If I would go now to the Einstein frame, because the relevant operator carries a scale, it is going to change. It's going to become time dependent, and the gap becomes enormous as a function of time. That is the result. So what would that correspond to in the bulk? In the bulk, it could either be a bubble of nothing, or it could be some situation where there was some extra dimension which went to 0 scale. These are situations which are very interesting, but not related to big crunches. So such a theory where the extra operator here is positive are interesting. They have an interesting bulk physics, but not related to big crunches. On the other hand, imagine now that the effective number is negative. And as I said, the effective number can become negative if the coupling in the microscopic theory is negative, it will remain negative. If not, we have the small g squared issues, which are, let's say, more peculiar, and also you have to ask yourself how they end up microscopically. So let's assume this is the picture. And let's say you have here a spontaneous breaking of the ON symmetry. So you have here n massless bosons at this vacuum. So this looks a totally David bread and butter theory on de Sitter. Nothing, no drama, nothing. Now take that same theory and map it using the conformal mapping. What happens here? Well, because the theory was stable, and because the leading operator was marginal, it won't be changed by the scaling, and therefore the theory will remain stable for any given moment where it is well defined. So that will remain the same. But what will happen to the configuration which was here in the minimum? So because of the anomaly which was discussed here also in Zohar's lecture, the R trace phi squared, there is a shift. And the field which in the de Sitter coordinate set at the minimum actually sits above the minimum. It gets shifted in the case of the Einstein coordinates. But now the couplings and the value of the expectation value of the fields becomes function of time. So the thing begins to go down, and the minimum goes down as well. So in a way, this system, for every given time when it exists, it looks like a system and a regime which takes very well care of its population, because there is always a safety network. The problem is that the safety network is going down, 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 down. And at a certain moment, it's going to explode. And these are the situations which are related to the big crunch. So from the point of view of the Einstein theory, yes, something dramatic happens. Couplings explode. Energies become minus infinity. From the point of view of the theory in expanding the sitter but with fixed couplings, nothing happens. It's just a usual story. Now, this picture, I think, also gives you a feeling why here we were able to do a complementarity map and in a simple way, while you can't do it in the case of black holes up to now. Because all the problem, actually, and the other ways to check it, come in the ultraviolet. So there is no need to use a renormalization group equation to feel the singularity. The singularity reaches the boundary, so you can probe it by the UV. And the mapping is all the time in the UV. So in such a situation, you don't mix scales, so it's much easier to build a complementarity map. And that's the reason I think that the complementarity map was found. Now, there is another situation, and that is a situation where the marginal operator has a negative sign. Okay, so when the marginal operator has a negative sign, that is actually something we looked at with Jose earlier. That actually turns out to be much more complicated. This situation, when the marginal operator on the boundary, either in Einstein or in de Sitter, because remember, marginal operators are not influenced by the conformal transformation, so what was negative will remain negative. In that case, this actually corresponds, if you wish, this is the field theory you get, which is the dual of the Coleman-de Lucia bubble. I didn't enter into detail into the Coleman-de Lucia bubble and its structure, but you can do a mapping which shows that when you have a Coleman-de Lucia bubble in anti-de Sitter, the appropriate boundary theory is one which has a negative marginal operator. And actually, the coefficient of the negative marginal operator is exactly what I told you in the beginning, the difference between the surface and the volume tension. So when you don't have a decay, that is when it doesn't help you, the difference in energy is not large enough relative to the surface tension, then you get a positive sign here. And you can show that when you can get a coefficient, a decay, actually this becomes negative. And you can make a mapping between the instantons, or bounces, let's call them, of Coleman-de Lucia theory, and what are called Fubini instantons or bounces in a conformal theory with a negative sign. And you can map exactly, by knowing the angular distribution of the coordinates and so on, you can go to the boundary theory. The problem is you have an infinite space, you have a lot of these bubbles, and the problem becomes extremely murky. So even though here there is an indication of a crunch which leads to an instability at any given time, you have an instability here, it's of a different nature and it's more complicated. Our conclusion when we looked at this first is the following. One question is when you have a crunch, if you need to cure it if you start it on a Cauchy surface which had a finite energy on it. If it had an infinite amount of energy ab initio, you don't need to cure the crunch. In any theory, also in a good theory, a crunch should occur. So, on the other hand, in a gravity theory, energy is not well defined. It's always, in a way, zero. You can play with boundaries and so on, but it's always zero. So how do you know if it's 1 minus 1 or infinity minus infinity? Should you get excited or not? So the great advantage of going to the boundary theory is that their energy is defined. And once you see that in the boundary theory, the transition is one of infinite energy, you realize that you are in one of those situations where it's true, you can't cure the big crunch, but it's its problem. I mean, it shouldn't have accumulated so much energy. Once it accumulates it, it's not your responsibility to fix it. But that is not the situation in what happens here. Here are situations where the crunch occurs from Cauchy surfaces with finite energy in one picture, which is a picture which gives you the answer from my point of view. You can live with it, and you just need a lot of patience, like infinite patience, to collect every correlation function. Calculate, calculate, calculate. Eventually, you will learn that you could tell the same story with a different narrative. So we live in the Middle East, where Judeo-Christian drama is all the time, Muslim is all the time. So that would be the Einstein picture of the description. But then you have Oriental cultures where everything is much more relaxed, no necessity all the time to have a drama, and that would be the dual picture of that. So I think I will leave this. Now, how do you get a feeling? Okay, so the conclusion to me is indeed drastic, because it changes. I'm not used to change points of view, and here I had to change a point of view. I had to change the point of view that singularities are big crunches, and I think I gave you a feeling of the classification of them. When a spontaneous symmetry breaking occurs, when you have many Goldstone bosons, and then a large negative relevant operator, you have big crunches. If you have a positive relevant operator, very interesting physics, but it's not big crunches which occur. So there are situations where the theory can just live with it, and we have to accept it. Now, it could be that the theory does something else, because it wants to, because of other ingredients that we are not aware of. And here we found that that means in particular that the OD, 1 symmetry, which I discussed, has to be broken down to an OD, U1 symmetry. And it also means that the sitter has to have a finite lifetime. Now, it could be that eventually all the fears are correct. But at this stage, I don't think we have much evidence for that. So here is a situation where I could present you a complementarity map. I'm telling you it happens because everything is happening in the UV, in the large field behavior, very large energies. That's where the action happens. That's why you can do a UV mapping. And in this case, even an infinite amount of entropy can be handled by an observer. So if you don't have to insist to work with a Hamiltonian which lives a finite time, like the one in Einstein, you can work in de Sitter. But you can also have much more excitement and work in the Einstein framework. But again, not waiting for a white knight to solve that problem. Because you can handle also the large entropy. So I think I gave you here two examples of lessons that can be learned from emergent gravity. Because the answers, if we like them or not, were not obtained in the framework of gravity. In the framework of gravity, we try to formulate the problem and make the connections. But the results were obtained in the framework of the system, which had no gravity inside. So in one case, I think the result was not surprising, even though it resolved a problem which some people were worried about, wrote books about, were worried about for a long time, and some people were not. But it was definitely a problem which bothered theoretical physicists. The second problem, I think we are just at the beginning of trying to understand how this works, and probably, even if I think of finite time Hamiltonians, it's obvious that a picture of emergent time is begging itself to come to describe such a system. Because where did it start for? Where did it end? So emergence and destruction of time are really requested to get a much better handle on what is going on here. That's it.
Both for the problem of the black hole and for this problem, the white knight is not needed from the point of view of the outside person. The white knight is needed from the point of view of the poor unfortunate soul heading towards a singularity.
Right.
And not saying anything about that in either case.
No, I'm talking about, but I think it wasn't obvious from before that in a big crunch, there is a situation where there are people who don't need the night. Because the big crunch reaches everywhere, I was in a situation that everybody needs the night. And now we found that one description goes to Las Vegas.
I agree, but the person who doesn't need the night is the person who's running away from the bubble all the time. Faster and faster and faster, so they always stay outside.
Let him change his chord. Let him change his picture. He has to change his picture. I can't help him, but okay. But the fact, again, that somebody doesn't need it must teach us on the way that eventually how the...
I see this as entirely analogous to the usual black hole story.
Okay.
It's just,
you
have more symmetry, so it's not you get an honest FRW crunch rather than these tiny crunches that you get inside black holes. But the essential conceptual points are identical.
I totally agree. The only place where I said in the beginning, I think the difference is in the amount of entropy still.
Oh, I agree. Sorry.
There is finite. So, you know, we got used to compromise on finite, but we have to compromise on infinite. That's more. So that's why I emphasized that as well. Okay, so I want to thank the audience for coming, being such good students. So thank you for coming.